I think we can wait like a couple of minutes. Are all of you coming from work, home, or another class, home? Work? Who's coming from work? Wow. Have class? From home? Okay. 2 from home? 3? Yeah, imagine when the World Cup starts, what will happen with the traffic? Maybe we should reallocate all classes to somewhere else. Yeah, next summer. We never know. It might start earlier than that. They should decorate the university for that. Yeah. Okay, I believe we can start now. So welcome everyone again to the 6th lecture. It's really moving very quick. And hopefully we already digest all the material related to cache memory in the computer. So hopefully now you are a bit more expert about how we design a cache, what are the software side, what are the hardware side, how to reconfigure the replacement policies, for example. We discussed last time several of these policies. So which one of them was the best or optimal? None of them, right? So each of them really depends on the pattern, depends on the type of messes that we are going to have, which is really hard to predict. It's hard to tell whether this is isolated or parallel mess. Which one was optimal for isolated messes? Which one was optimal for isolated messes? MLP, aware replacement policy. MLP stands for memory level parallelism. Which one was optimal for any type of messes in general? LED optimal algorithm. And which one was normally used in modern processors? LRU. Least recently used block should be replaced, right? But normally we don't implement it as the true one, the actual one. We have variant of that, heuristics of this version, because it's very expensive to be implemented because we need to keep track of all these blocks. So we need to add bits that can accommodate the entire map of the cache in order to be able to know which one was least recently used. Okay. All right, that's something really nice. At least you keep track of all the material. So this is the goal of why we record all the lectures, although the attendance is really mandatory. And hopefully you enjoy the slides. How many of you was already aware about all the things we discuss about caches? Have you seen it before? Have you watched it in YouTube before? Study it? Okay. All right. That's really nice. So memory is really the major part in today's CPU. There are a lot of products even coming every year, changing all the RAM that we are aware of. So they change even the mindset about the memory. So we start with the 2D stacked or 1D stacked memories, and these days we jump into what we call 3D stacked memory. So instead of having a single layer of memory, now we stack them on top of each other. And this is changing the way we design these memory systems. Today so luckily we're already done with cache, no more caches, but hopefully we'll jump into caches toward the end of memory system. Today we'll focus on what we call main memory. Okay, so we are done with everything inside the CPU in terms of memories. Now we are going to the off-chip, off the CPU memory, which is the first level is the main memory itself, which we call as RAM or DRAM to be specific, because there are a lot of types of RAM. Cache, for example, we call it SRAM. Okay, so RAM alone is not enough. So what we use as main memory normally DRAM. Okay, and sometimes we call it DDR, double array. All right, so this is to recall. I really like these slides because give you the full insight, the full picture of how computer system understand your command. So normally we start with the source code, which is normally in human readable format. You write it in C, Python, Java, in any language, and then you use a compiler to compile, try to find the error. Once there's no error, it will convert everything into what we call as assembly language. Okay, and the assembly language is different from one machine to another. There are different instruction set, different format of those instructions, how many bits is dedicated for each variable, for example, how many bits dedicated for the operation itself, how many operand, and so on. Okay. Once we have the assembly language, still it's not low level. It's not what the machine can understand. This is kind of low level, but not really the lowest level that can understand your hardware. Okay. So that's why we have to move it to something else, which we call the machine code. And machine code is really what the machine will understand and can act based on every single bit in those data. So we convert the assembly to machine code. And the machine code, again, all those division, normally it's transparent, it's isolated, it's hidden, you cannot see it. And those division is basically based on the architecture that you are targeting. So the number of bits here is not fixed. The number of operation, the instruction, and so on are not fixed. Once we get the machine code, we go to the CPU, and we try to process them based on those bits of zeros and ones. Okay, we're going to jump into the CPU after the main memory. So don't worry about what's happening here. But hopefully, all of you study already computer architecture during undergrad, which you go through the ALU, and this simple CPU, which we call single cycle CPU, because it can fetch an instruction in single cycle and can execute it and then write back to the memory. Now we are still a bit one layer on top of the CPU, so we didn't dive deeper into the CPU. And what we can see from the top level, we can see that there are several levels of caches. And then we have the main memory, the storage, maybe some remote storage if you are using cloud, and so on. And now we'll try to focus on what we call random access memory. All right. We call this entire thing as hierarchy, right, including the register and the CPU. And we already reason why we use hierarchy instead of just the storage. Why not just having one big storage, a CPU, and that's it, right? All of these are very expensive to implement, and you can imagine the storage in kilobyte or megabyte, and they are really expensive. What if we move to gigabyte or terabyte? That's why we have this several levels of hierarchy until we jump into the main memory. Now, if we talk about computer memories in general, they are grouped into two types. One of them, what we call primary, and the other as secondary. And that is the accurate name. Why? So primary means really essential. Something without it, we cannot operate. A computer without main memory will never boot even, okay? But without the storage, we could do something. So we could have remote storage, for example. We could have different type of storage. But without the main memory, there's nothing will operate. That's why we call it primary, and that one is secondary, something second level, okay? So when we talk about primary, we have the RAM, which you already mentioned it, right? And we have a ROM. So, and what is the difference between RAM and ROM? Raise your voice, please. Permanently stored. Excellent. Yes, that's correct. Temporary means depends on. Excellent. Which is volatile, right? That's what we call as volatile memory. So the ROM, why we would use it? Why we would use something that permanently stay there, holding the data? Excellent. Not the operating system. Something related to the operating system. What is it? The operating system always in the storage, right? It's about 7 gig. You cannot hold it in BIOS, for example. What do we store? No. Go back to the operating system. What do we store? Something related to the operating system. Okay, we have the program that initiate the computer. What else? How we initiate the operating system, how we turn it on, how we activate. So when we turn on the machine, doesn't know where's the operating system, doesn't know anything about it. No, it tells you something about the operating system. It tells you where is the operating system located exactly and how to load it into the memory. Okay, so it tells you the exact path of the operating system. So it goes to the BIOS. Every time you turn on the machine, go to BIOS. It initiates a lot of things related to the clock, the time, the path, the full path of the operating system, the storage, where to initiate it, and so on. Okay. And the operating system then will take over, try to manage the memory, all the requests, how we map the virtual memory or the physical memory into virtual memory, and so on. Okay? So that's why we need something permanent that even if we turn the machine, it's still there. Okay? And every time we install a new operating system, it will go to the BIOS in the ROM and try to modify it. Okay? So it's modifiable. It's not like once we write it and then done. This is what we call BIOS. Okay. Now for the RAM, which is volatile, volatile means doesn't hold whatever is stored in it. Once you take off the power plug, then done. You'll lose everything in it. Now for the RAM itself, we have two types, SRAM and DRAM. What is SRAM? What is it? What do we call it last time? For 3 lectures, we've been talking about it. Caches. So SRAM is a cache memory, okay? And what is made of? What is the smallest building block? Transistor, okay. How many of them? 6 transistors, excellent. And they are basically building the D flip-flop, okay? So 2 D flip-flop to hold 1 bit, okay? Excellent. You need chocolate? Can have one. All right. Thanks. So the SRAM is much faster than the DRAM, but more expensive. In the DRAM itself, we have different type of DRAM. How many of you are aware of any type of DRAM? Look at the last line, for example. Are you aware of any of them? Which one? DDR4, excellent. That is a bit older generation. What is currently? DDR5. This is the latest, okay? DDR5. However, you might hear about DDR6 and DDR7. What is it? Where can you see DDR7, for example? This is the latest. This is the latest in any desktop server and so on. But there exists DDR7. What is it? No. No. Not yet. It's called GDDR7. What is it? Graphics DRAM 7. So there are two types of DRAM. One of them for graphics, and that exists in almost all GPUs. Okay, and it's a bit different than DRAM. The architecture is somehow same, but there are essential differences. The main difference between GDDR or DRAM and the DDR is the number of pins as a chip. So this chip has limited number of pins. The other one is much bigger, has a wider interface, a lot of pins. Why is that? To enable high data transfer between the memory and the actual processor in the GPU. Okay, so those really much faster than what we have in DDR. Okay, all right. Hopefully, this kind of giving you the full overview about memories. We already talk about SRAM with caches. Now we'll focus on DRAM, and hopefully we'll cover the storage at some point. All right. Now let's jump into what we call as a DRAM device. And this is really important topic. We already went through what we call AMD Barcelona CPU. Okay, this is very old, 2006, but it gives you a really clear perspective about how the CPU is made of, what kind of cores, the number of caches, and so on. Because the size of the core were really huge compared to the ratio of the CPU, and so with the L caches. So you can clearly see the cache, the cores. There are 4 cores. There is L3, which is shared among all cores. Okay, and then we have what we call DRAM interface. The DRAM interface exists inside the CPU, and that is responsible for communicating with the DRAM itself. This is the DRAM device. Okay. Now, we discussed several times, whenever we want to get any kind of data or block from memory, who's responsible for that? The memory controller. So the memory controller unit, which is located inside the CPU. Okay, that component already inside the CPU itself. And that is responsible for issuing any kind of command to communicate with the DRAM itself. So if you need any kind of data, you send a command to the DRAM through the memory controller, and the DRAM will respond with the data. The data will go to L3 cache, then to L2, L1, and so on. So those controllers in the old days, they were located in the motherboard, okay, as in the BIOS, for example. Okay, so it's outside the CPU in the old days, especially with the microprocessor and the special purpose CPUs. As the first general purpose computer, in 2003, they start adapting the controller inside the CPU. So it was before that adapted already inside the CPU as in microcontroller or microprocessor. But the general purpose CPU that implements it inside the CPU was an AMD K8 in 2003. And the reason behind that was to reduce the cost of off-chip round trips. So imagine every time I need any kind of data, I go outside the CPU, I contact the controller, then the controller responds back, okay, on it, I'm in the queue, right? And then the controller, which is outside the chip, send back to DRAM, which is another component outside the chip, and then they send back the data. Anytime you go off chip, it's always expensive in terms of communication because the interconnects are bulky and there is a lot of noise, a lot of energy to send data through the interconnect, especially if it is outside the chip. So that was the reason why they bring that component inside the CPU. So now it makes the CPU bigger because it takes some space, right? But it saves a lot of time, a lot of energy to communicate with the outside world. Now, the DRAM stands for Dynamic Random Access Memory. We already talked about this. We consider it as temporary storage for data programs that the CPU needs to access quickly. It's considered volatile, meaning it loses its stored data when power is turned off. What is important is that this technology uses one capacitor and one transistor to store a single bit. So every time you want to store any single bit, you need these two main components, a capacitor and transistor. The capacitor, as it's clear, it's always responsible for storing voltage. Okay, that is the main function of any capacitor. That's why you see it, for example, in the electrical tower in the street, for example, you see those big cylinders. Those are capacitors, are responsible for storing some kind of voltage. So whether the capacitor is charged or discharged indicates a storage of 1 or 0. So charging that capacitor is a binary of 1, right? And discharging the capacitor is considered as binary 0. Why we need the transistor? Let's see. Please pay attention to this visualization. It's really important. Now, this is the capacitor. This is always the icon of capacitor. Okay, when I ask you to draw a capacitor, you should draw it this way. Those two lines should be equal in length. Okay, this is how the capacitor is drawn. Now, since we want to charge it, you have to connect it to a source of voltage, right? So once you connect it, you already charge it, and that's considered as 1. Now, once you disconnect it, then what will happen? Excellent. It will not discharge quickly. The charge will remain there. And that's the main function of the capacitor, to hold the charge, even if you disconnect it from the source. Now, if you connect it into any source that requires energy, for example, like light, it will turn on, okay? Because it's now acts as a battery. However, there is a huge fundamental problem with capacitors. What is it? Charge discharge time. It's not a real problem. Direct? Sorry? It's not really a big issue because this is what we really need, right? We need binary, 0 and 1. So DC is good for us. What is the problem? Let's see. What happened? Leakage. Who said leakage? Excellent, John. What happened? Someone drinking that juice, right? What happened? Keep reducing, right? Now it's already exceed the threshold, right? Become a 0. What happened? What happened? Done, right? It's gone. So very fundamental problem with the capacitor, it leaks charge over time. Not really soon, not within a minute and so on, but it leaks over time. That time period, we have a definition for it. We know the amount, the interval that we need to do something for it, and we are going through that interval, okay? However, let's say just over time, it loses charge. Now, yes, please, you have a question?
Yeah, is it similar to like a hybrid battery, but as the capacitor fills up the charge and holds it and stores the battery?
Yeah, but that happened over years, like 50 years. But here, it happened over fraction of seconds, okay? But we will see it. We will see the exact amount of time needed to do something about the charge. Now, we can exploit that device, capacitor, because at the end of the day, it's really small, right? So we can have a large quantity of that device. So that's why we are using it here. But however, the problem, how to control, when to charge, when to discharge. That's why we need a transistor, right? So the transistor normally is used as a controlling gate. You allow for the charge to pass to the capacitor, so it starts charging, or you disconnect it from the source, so it starts discharging. And that's why we need really capacitor and transistor to store a single bit. All right, now we want to build the memory. So we bring those capacitor and transistor, and we have large quantity of them, right? We just keep stacking next to each other until we get very large memory. Now, how far we can go? And what is the arrangement? What is the best arrangement to have all those building components next to each other? Why? Please close all laptops, unless you are in stock market again. Yeah, please close, 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 all of it, all of it, all of it. Why 2D? Why as rows and columns? All right, that's a very good way of thinking. We need rows and columns. Yes, there's the answer. Okay, you are there. What else? Less space. Excellent, that's a good point. What else? Yeah, really, we have nice ideas now. Okay, all of it correct. Now let's see what happened. So we have a problem that if we have single large array, right, we could like have thousands of these components to store thousands of bits, right? However, there's a problem. So it takes really long time to access this entire array, because every time we need to charge, discharge, and access the bit and detect whether it's 1 or 0, it's charging or discharging, and then do this many times. So we need many of those sensors, right, to detect whether the charge is there or not there. And that will take a lot of time. And the second problem is scalability, how to scale this memory. So we can build very long line, means every time we want to access the memory, we need to fetch the entire row, right? There are no multiple rows to store the data. If I need certain piece of data from that array or sub-array or certain number of elements from the array, I need to access the entire thing and then fetch those components. So our goal is to reduce the latency of memory array accesses and enable multiple accesses in parallel. What does it mean? It means if I have very long line of those elements, right? I want to access this portion, and then this portion, and then this portion, and so on. What should I do? Divide the memory, right? Excellent. So now if we have, instead of one row of those elements, I have now 2 rows, 3 rows, 4 rows, and so on. And every time I can access the entire row, I have no problem with scalability. I can really grow in capacity much faster than I have a single array. And the other thing is that the hardware I use to sense or to detect the charge for one row can be used as is for all rows, right? So I can multiplex the same component or the same sensor that detect the charge if it is in the capacitor or not. I can use exactly the same sensors to this row, for example. So every time I access one row, I don't need to connect it to multiple rows. I just connect here, sense the charge, give me the data, then disconnect, connect here, give me the charge, give me the data, and so on, right? So I save a lot of space, a lot of component hardware, and that is the price you pay for the memory. So the idea is really to divide the large array into multiple banks that can be accessed independently. And that's very important, because if I can access all of them at once, that's really a problem on how you could transfer this amount of data into the CPU. You could access, let's say, how large the DRAM we have in devices, 32 gig, 64. Imagine we access this entire thing, the whole thing, and want to move it to the CPU. So we lose the sense of having caches. We no longer exploit those cache devices. So we'll see that in visualization, which will give you better insight about what's inside it. So now we consider 2 main points. Each bank is smaller than the entire memory storage. Now we have a new term called a bank. Now we will see what is it. And accesses to different banks can be overlapped. The key issue, how do you map data to different components of the memory? Now you divide the hardware of the memory, but now how we move a data from storage, SSD for example, into the main memory. How we can really define the layout for one piece of data. The data is 1 meg, for example. then how to divide it over these rows. And if you have multiple of those components, how you divide a larger data into multiple components, not only multiple rows. Okay. Ultimately, we wanted this row, and then another row, a third row, fourth row, fifth row, and so on. Right. This way, we can have a small area of memory. We can store large number of bits. Now let's jump into the details of that DRAM device and see those arrangement that we talk about. Now, your colleague said the best arrangement is to have a 2D array, meaning that we have a table or a matrix, and in every cell we have to store a single bit of that, right? And then we have some address that told us where to access or which exact row, which exact cell to fetch back. Okay. And then we also have for columns to tell us which column we really need from the memory that's stored there. And that's the beauty of having multiple of rows. You can see the row decoder, for example, and the column decoder are shared among all cells. We don't have really to replicate the column decoder, for example, for each row. So just has the width of single row and shared for all entire rows. So all rows are connected to that decoder, for example. Now, why we need these decoders? First of all, there are 3 interfaces connected between the CPU and the DRAM. Those 3, we call them buses. One of them responsible for data, right? Transferring data between the memory and the CPU or the caches. And the other one called address bus is very important to tell us where to find the data. And the third one is the control or the command, basically. When we send the command from the controller unit, it should go through dedicated path to tell the memory do this and do that. All right, now let's see the visualization. I think you will get a clear insight about what it's made of. First of all, what's this? This is the DRAM, right? If your computer is slow, you would go to the shop and buy one of those and plug it into your motherboard, right? This is how it looks from outside. There are some pins, those for communication, and there are some pieces over there, the black, which are chip, those where we store the actual data, right? Now, it communicates with the CPU through what we call the memory controller. And what is connecting the memory controller with the DRAM, we call it as memory channel, okay? Now, we call this entire thing as the memory device or a DRAM DIMM, D-I-M-M, okay? Now, the DIMM itself has multiple rank. So, for example, in this picture, we have 2 rank. We have all these chips together, 4 of them as one rank, and the upper level or the top level as another rank, okay? Sometimes we have many of them. We have 4, 8 ranks, and so on. Now, if we look into one of these chips, which we call DRAM chip, so we have many of them, right? They are divided into 2 ranks, and each of those ranks has many of those chips, and the chip itself has what we call banks. So single DRAM chip has a lot of those banks. Now, if we look into the bank itself, what is inside it? Now we can see kind of a matrix of those cells. However, the matrix, to make it really big, we cannot have one single matrix. We divide it into sub-matrices, which we call sub-array. Now, when we look into a single sub-array, we will see the actual matrix we discussed in the previous slide. Hopefully, it's clear. We have the channel connecting the DIMMs. We could have more than one DIMM, right? We could buy those multiple DRAM devices and plug them into the motherboard. Then for each of them, we need a separated channel to communicate with the DRAM. Now, for the single DRAM DIMM, we have multiple ranks. A rank means a group of chip. And those chip, if they consider as single group, meaning that they are sharing the 3 communication interfaces that we just mentioned, which is the data, the address, and the control. I mean, these three things are shared among all those chips in the single rank. Okay, every rank sharing those separately. Now, in a single chip, we have the chip. We have, multiple of banks in a single chip. And within a bank, we have many submatrices. And within a single subarray or submatrix, we have the entire matrix as a rows and columns. Now, every single element over there, we call it as a cell. And the cell has one capacitor and one transistor. Okay, is it clear? Now, in a single cell, we store how many bits? 1 bit. So every single cell over there, we store just single bit. Any questions so far? Okay. Let's see it in the hopefully next lecture. So that's a very important question. What is the bandwidth, for example? What is the amount of communication we have between? How to access the cell in first place, right? How many cells do we have? How many rows? How many columns? How many banks? All of these valid questions. And that is really depending on the technology that we are using. So it's really different from DDR4, from DDR5, DDR3, and so on. Okay, but we will see some examples today on all those parameters and the frequency, the bandwidth, and so on. Okay. A single row in the matrix, we call it as a DRAM row, which makes sense, right? Because it's a row of bits. However, the granularity of accessing the subarray is at what level we can access the subarray. Is it at rows level, columns, cell level, a group of cells, for example? Every time we request data, what do we have access to? Is it single cell, 2 cells, 3 cells, single row, single column? Who says row? 1 row. Who else? 2, 3. Who say column? Yeah, excellent. We access it at the granularity of rows. So every time we do one access, we access the entire row. Okay, that's why it's very important to remember this is a DRAM row. Now we have what we call a bit line. It makes sense. Why a bit line? Because we have bits over here stored. So every time we access the entire row, but we cannot access the entire column. So we cannot call this as a column. We call it as a bit line, because a single line accessing a single bit. Horizontally, we access the entire row. Vertically, we access only a single bit in that row. Okay? That's why we call the horizontal line over here as a word line, because that is a wire connecting all the bits in the row. Okay, so we have a word line and a bit line. And to make sense, actually, why we call it like that. So if you're ever in doubt, remember a bit, because we connect the wire to a single bit. A word line, because we connect more than bits. It's not a word per se. It's the entire DRAM row or entire interconnect or entire wire. All right, so we go from top level to the down. Channel, DIMM, rank, chip, bank, row or column, and then all the way to the cell. We cannot access the cell, okay? So we access the row level. Sometimes we can define the columns that we are going to access. But first, we have to access the entire row and then fetch it. And then we could access the columns in that row, okay? All right, so we saw that picture with the capacitor and transistor, but now let's see it in action. Let's see how we sense the voltage itself. So now we have a capacitor. Remember, this is the shape of capacitor, just 2 vertical lines, and we have a charge in it. And this is the transistor. This is basically MOSFET transistor. So we have source, gate, and drain. And we have ground over there. We have here what we call as sense amplifier. Sense amplifier. And this is the sensor that we use to know whether this is charged or discharged. Okay, that's why we call it sense. And the amplifier has a meaning why we call it amplifier, because it amplifies the signal that we got from the capacitor. So every time we access the charge, we amplify it into a certain voltage level, so it's easy to sense it. Okay. Now, what is connected over here is what we call a bit line, because it's connected to the bit over there. Okay. And what is connected over there is the word line. It's connected to this, to the gate, or to the transistor, but also it's connected to all transistors in the same row. So this word line is connected to all of them. But this one is connected only to this one in this row. This is a word line, this is a bit line. Okay. Now we have a negation of the bit line. We don't have to worry about that. They're just differential amplifier, so that's why we have the positive and negative. Now, if we enable the sensing, meaning that we open the transistor, so the charge will go through the sense amplifier. This can be open or closed. Now, if we open it, it means we connect the capacitor to the sense amplifier. And in the sense amplifier, by default, initially, we have half of the voltage value, So normally we connect either VDD, right, which is like, could be 5 volt value, or a ground. We draw it like this, or sometimes this is a ground. Ground means 0 volt. Okay, so any circuit normally needs voltage or ground to operate, right? And this is exactly what we have here. However, what we have in the DRAM is half voltage, okay? Half of the value of VDD. Why is that? Why not VDD, not 0? Let's see. Remember, this capacitor is charged. We have full VDD in it, okay? Now we enable the word line, meaning that I enable the entire row. So now I know all those transistors connected to all other cells. Now it's connected to the word line. Now I connect the bit line, meaning that I start reading this bit. Okay, the transistor is open. Now what happened over here? This is before, this is after. What happened? The charge decreases. Why is that? Remember, we have VDD over there. When we connected the sense amplifier, we have half VDD. Now, the bigger charge should move to the lower charge. If it is 0, it will drain fully. So the entire charge will go to 0. Now, because it's not connected to 0, it cannot just go away. So try to do a balance between the half VDD and one full VDD. It went a little bit down, and that half VDD should increases, right? Should increase. Why? Because now we are sharing the charge between this, the capacitor, and the bit line, and then we can see an increase in the original or the default VDD or half VDD that is caused by being fully charged, right? Now, imagine if the capacitor was not charged at all. What will happen? We have half VDD, we have 0 over there. So either a little bit of that charge will go to the capacitor, right? Or it just remain empty, and that charge will never get increased because we have 0 over there and we have half VDD. They are not sharing the charge anymore, and then either to remain as half VDD or sharing the charge with the capacitor and still get reduced less than half of the VDD. Now, what is the problem with half, or what is the good thing that we are relying on half VDD? So if we increase that baseline by a little bit, then that's an indication of a charged capacitor, right? Because it was 1 or full VDD, then we are sharing the charge with the half VDD and get increased by amount, okay? Now, if it was not charged, then we get less than the baseline, which was half VDD. And this gives us kind of indication it was either 1 or 0 That's why the charge either increase over the baseline, which is half VDD, or less than the VDD, right? So this is how we can sense whether the capacitor was fully charged or storing a bit of 1 or storing a 0. Now, the fifth step is just to enable the sense amplifier to sense the perturbation over there, whatever the charge was there. And then the sense amplifier can tell you whether this is 1 or 0 based on amplifying that value and then record it as another voltage value and then pass it to the CPU as either 1 or 0 through the data control or data buses. Okay. Now, hopefully this mechanism is clear to you. So we have a capacitor, we have full charge over there, we have a reference as half VDD. Every time we enable the bit line, meaning that we access the capacitor, either we get some charges from the capacitor, so we can know that now it's exceeding the baseline, so there was something stored already in the capacitor. If not, then it means it was stored as 0. Now, there is one problem that we already miss with the capacitor charge. We already play with it. And we said those are main memory devices, primary device to store the data. Now, if we are playing or perturbing those charges, what will happen with the data? So next time we read it, if it stays like that, and next time we enable the bit line and want to read it again, the charge might go down again. Go down until we go less than the baseline, and then the value changes from 1 into 0, right? So the data was not correct anymore. So there is one step we have to do to fix that. We'll go over it in the next few slides, but now hopefully, yeah, it's clear here, but we'll go over it. Something we have to fix every time we read those capacitors, okay? But remember that in few slides, we should go over that. All right, so now let's go over some terms. Hopefully now you are clear with the channel, DIMM, ranks, then chip, banks, subarrays, all the way to columns and rows. A DRAM bank is a 2D array of cells, has rows and columns. Each row is called as a DRAM page. This is not an accurate naming because the page, we use it normally in the storage, in the SSD. Whenever we get data from the SSD, we fetch a whole page. However, in DRAM, we fetch only a row, the entire row. But sometimes we call it with the same terminology of physical storage as a page, okay? But still, a page is a row. It's not a 2D array, for example. The sense amplifier is also called as a row buffer because we have one sense amplifier per bit, and every time we access the entire row, if the row has 16 bits, for example, how many sense amplifier do we need? 16. So for every bit or every bit line, which is the vertical connect, we need single sense amplifier that sends the charge in a single bit. Okay? So if we have 16 bits in a row, then we need 16 sense amplifier to capture the charge in those 16 capacitors. When we talk about addresses, of course, we need the address of the row and the address of the column. Okay, why is that? Because again, the DRAM subarray has rows and columns, and to access a particular column, as we said, we cannot access the column directly. We have to access the entire row first, and then we get the array in the sense amplifier or the row buffer, the entire row, and then we could access something out of it. Okay, so that's why we need the address of the row first, and then the address of which particular column in the row, and then we can get this data, send it through the data bus to the CPU. Now we have two types of rows in the DRAM. One of them called open, one of them closed. Okay. Every time we want to access a row in the DRAM, we have to open it first. What does opening mean? So opening a row means activating it. activating it. It means connect the word line. The word line is basically a wire. Okay, the whole wire can be connected to any of those rows. Can be connected or disconnected. So we connect the entire word line, which is horizontal line, to the entire row that is required based on the address. So we send the controller, the memory controller, send an activate command, okay, to open a particular row based on the address that is sent through the address bus. And then we do a second step to read or write the data that we need for that particular row. So we already have an address to the row. Now, do we need to read it or write it? Let's assume we read, because of the previous example, we just saw how to read the entire row. So let's assume we read that row, which means we activate the sense amplifier, and we get the charge from that row into the sense amplifier. Now we can know that whether there was 1 or 0 and so on based on the values in here. Okay. Now we read, we got the entire row, but we miss with the charge of the capacitor. And this is not for single capacitor, but for all capacitors in that row. So all of them now, we perturb the charge over there. And if we keep opening again the same row, we keep reducing that charge. Okay. So now we have to do something which is called as a pre-charge, meaning that I read the entire line. Now I moved the charge over there, or I took part of those charges into the sense amplifier. Now this is no longer valid value, but I have here a valid value. All the bits over there are correct, but the bits over there already perturbed. So what do I need is to write back everything in the sense amplifier to the same row. And that is happening every time I access the row. Every time I need to read it, I open it, I activate it, I move the charge to sense amplifier, I get the data already to the CPU through the data bus, so I already got a copy of it. Now I need to close back that row, meaning that I pre-charge it with the value that I have here in advance. That's why I call it as a pre, right? So I move the charge from here back to the row to maintain or sustain the correct values again. So now every time I want to open the same row again, I find a correct value of those charges, right? Because I already moved the charge back into full VDD as fully charged in the capacitor. So now we talk about closed row. How about a row that's already open? So imagine that I open a row, I read the value, it's already in the row buffer. Now another time, the memory controller told me, give me the data in that row. The row was already open because the data is still in the row buffer, right? I could say, okay, wait, memory controller, I cannot respond to your request. Now I have to close the row again, and then I will read it again. Yeah, of course, when closing mean pre-charge, okay? So you have to wait until I close the row, and then I will open it again for you and give you the same data again, right? But sounds really not so smart. So I open the row, give you the data, I close the row, now I open it again and give you the same data again. So there is something smart with the memory controller. It already has a kind of low memory to remember what kind of request I already sent to the memory. So if I send you a request to read a data at the same address again, then I don't have to close that row again, okay? And this is how we call that row as open. So I could access it as open row or as a closed row, right? If it is already open, it means the data it's already in the sense amplifier. I don't need to do anything in the DRAM. Everything is good for me. Just send me the data again. And that saves a lot of time by not activating and sensing the charge and moving again, closing the row, and so on. So it could allow me to read the same data again, which is accessing an open row, and no need for activation mode. However, if now I'm moving to another row, I directly need to pre-charge to return back the charges to that row, okay? And then I can move to another row. All right, now we didn't discuss about leaking the charge. So we talk about reading and then returning back the charge and keeping or maintaining or sustain the original status of the DRAM. But we didn't talk about the problem of leaking that charge over time. Even if I'm not touching the DRAM, I'm not reading any value, right? I just keep it there for 1 hour. What will happen? Start losing all the data. And then once I request, miss all the hierarchy, I need to go back to the storage, get back the data to the DRAM, to the caches, and so on, right? We will see it in the next slide. But now, let's focus on how we read the entire row again, because we talk about accessing one bit line, one value, one cell, and get a single bit value from that. Now, back to our matrix. Remember, when we talk about matrix, mean a subarray or sub-matrix in the entire bank. Okay, we have in the one bank multiple subarrays, and now we are talking about single subarray of that, which has all the rows and columns. Now remember, the granularity is to access the entire row. We cannot access single cell. We cannot access single column or multiple columns. We have to access any entire row, and that's the address you provide from the memory controller. So assume we are given the address of the first row, or in computer we call it first row because 0 and 1, or we can call it a second row. Okay, so we activate it, mean the word line, it's connected to the entire row. And now within the word line, we have many bit line, each of those lines connected to single bit in the activated row. So only it's connected to that particular cell. Now remember, in the bit line, we have the charge as default is connected to half VDD, okay? Now every time we have, so those are isolated, are not connected to each other. The orange lines are not connected together. So a single charge went to vertically to any of those lines, not shared among all the other lines. That's how we maintain the value stored in a single cell. So we have here what we call as a row buffer, but remember, row buffer is sense amplifier. The row buffer is sense amplifier. So it's responsible for two jobs. The first one, sensing the voltage, and the second thing is amplifying the voltage value. The second step, read or write. It depends on the process or the command that's coming from the memory controller. Assuming here we are reading, so we got all the data to the row buffer, and now based on the address we provide for the column, we can access any column we want within that row. But remember, we cannot access column. We have to access the entire row first and then get any column within that row. Okay? Once we are done reading and we are sure that the memory controller is not going to send us to read command for the exact same row again, we pre-charge the entire row with the original value, and we are done with the entire thing. So we went gradually with those 3 steps for single cell. We saw how it works for single capacitor, and now we see already how it works for the entire row line, right? Which is DRAM row. Now, I promise you to show you how we can fix the leakage problem. Let's see it together. Assume we are not reading now anymore. Okay, we just leave the DRAM for there for some certain of time. We already have a charge in some of the cells, not all of them are charged, right? We have a lot of ones, a lot of zeros. Now we have full charge. Over time, start draining. This charge gets reduced over time. What we need to do? Excellent. We need to act as if we are reading the DRAM again. We are not reading. We don't need the data, right? We are not interested in reading anything. But because of the leakage problem, we have to every single row in the DRAM to access it again, get the data to the row buffer, to the sense amplifier, and don't move it to the data bus to the CPU because we don't need it. Just read that row, okay? Move it to the row buffer, pre-charge again to the row. And do that for every single row in the matrix. Imagine that. And this is happening if you turn on your machine and leave it there, okay? The CPU controller already knows when I should send what we call a refresh command. A refresh command. So every single interval, the CPU controller count that interval and then said, oh, now time to refresh the entire DRAM. Send a command, and within that command, I cannot request the DRAM to do anything for me. I cannot do read, cannot do write. So that refresh command should be serviced very quickly in order to make the DRAM available again for me to receive read and write commands. If I send refresh command, within very small amount of time, I need to refresh the entire DRAM, meaning that revisit every single row in the banks and in all banks to refresh all of them, and then I'm available to receive requests. There's a lot of research about that optimal interval. What is it? 1 second, 2 second, half second, and so on, or fraction of second. A lot of recent papers on that topic in particular. And not only that, they said refreshing all banks should not be equal. Okay, some banks might be exposed to more or longer interval than others. Even some rows need to be refreshed faster than others, for example, because the leakage in this capacitor is not homogeneous. Due to some manufacturer variation, all those capacitors are not the same. Some of them leaks very fast, some of them slowly, and so on. So you can emulate, you can simulate all those cells, you can do a lot of experiment, and because you know what type of data you have in the DRAM, so you can move the data yourself, so you already have a copy of the data, and then visit all those capacitors again. You have a for loop, just give me all the data again every once in a while. And then you can compare this data with the original data and see if the refresh interval that you choose was enough to get or to maintain the same data as is, or the data was changed because the interval you choose was not enough to refresh everything. Okay, so this is a very hot topic in how we do it. However, for current DRAM, do you have any question? Yes, please. Everything. I don't know which is empty, which is full. Okay, so I bring all the charge, but it makes more sense to not refresh them because anyway they are zero. So even if they lose charge, I don't care, right? Makes sense. However, it's kind of really hard to find the entire row as empty. Because remember, the size of the DRAM is much smaller than storage, right? So it's always get full. Moving any kind of application, you can get the 1 gig or 16 gig easily full. Remember, you have operating system working, you have many applications, you have Chrome, you have games maybe, you have videos and so on. All of them are in the DRAM and then move to the caches. So yeah, you could optimize, for example, the refresh interval to not be for those rows that were empty. But how do you know whether they are empty or full? You have to read them to sense amplifier and check all bits if they were empty and do something there. So it might require some hardware changes to the DRAM to know that in advance. Yeah. No, you cannot have the entire bank as empty, right? Because you should have some data. If the entire bank is empty, yes, you could do that. But it's kind of really difficult to find the entire bank as empty. Because remember, the 16 gig you have, it's for the entire DRAM, which has multiple banks. So each bank at the end of the day, about 1 gig or so. 1 gig is really not big enough to be empty fully, to not utilize it by the program. So it's directly get really full. But that's a nice question. And you'll see a lot of nice paper about choosing that interval. Now, for every DRAM we have in the market, we have what we call a data sheet. And in the data sheet, if you go there, you will see the specification. You'll see the exact amount of time that you need to refresh your DRAM in order to maintain correct data, which we call T refresh interval, T. This parameter, you'll see it in the data sheet of any DRAM you purchase. If you type the model number of the DRAM of the chip, not the DRAM itself, right? It's the same thing, but you have to be very specific with the chip itself to get the data sheet. So that interval in DDR4, which is not the latest, we already said that the latest DDR5, right? The interval is 64 milliseconds to get the entire DRAM refreshed. Imagine how fast. So 64 milliseconds to get the DRAM refreshed. If it is longer than that, then it's a problem, because remember, when we refresh the DRAM, it cannot be available for your request. We cannot read, we cannot write. So it have to be frozen, everything. Memory controller will wait until it gets refreshed and then send more commands. So that, lucky enough, that interval is really small, okay? But still a problem, because 64 milliseconds, it's a thing compared to the processor speed. However, there is one hack over there. If the temperature of the DRAM device get higher than 85, the temperature get higher than 85, then that interval should be half, 32 milliseconds. Why is that? Because capacitors leaks faster with high temperature. That's why, if you remember the CPU we had in the motherboard in the first lecture, what we have on top of it? Heatsink and a fan. Because remember, temperature is going to destroy not only the electronics, but also the information. The data itself gets leaks quickly. So we lose those data. And that's happened at the CPU side. At the DRAM, especially the new ones, what do we have? We have temperature sensor inside the DRAM itself. Okay? How I would know if the temperature is high or low? How I would choose interval for that? So we will see that, especially in the DDR5, we have not one sensor, two sensors. Paired them to monitor the temperature of the DIMM itself. Okay? And based on that temperature, either we choose this interval or the other interval. So this entire process we call as DRAM refresh is the key maintenance operation to avoid bit flips due to charge leakage. And as Jahin said, this is a problem for those who are stored as value of 1. If this value of 0, it cannot leak more, right? It's already reached the minimum. The DRAM refresh activates a row, pre-charge the bank. Remember, there's no read, no write process. I just activate the row, get the value into the row buffer or the sense amplifier, and move it back. So read it, amplify it, send it back to the row. That's it. This is the refresh. And I do this for every entire row. Now, do I need to do it for all banks at the same time? No. So you could start one bank now. You get the data, activate, move, store the data, refresh. Now, the second bank might not be getting the data at the same time as the bank 1, right? So from the time I move the data to bank 1, I start counting that interval. So they are not necessarily all banks get the data at the same time. So that's why I don't need really to refresh all of them at the same time. Some of them will have junk when I start the DRAM. It's not necessarily to be reset to certain value. So in some DRAM, I get true data. And this is where I start counting the actual time interval to refresh only that bank. And then for that amount of time, it will be much less than that. So this time only for refreshing the entire DRAM. If I go a granularity of banks, then I should get less than that time, and so on. The DRAM refresh blocks accesses to the whole bank or rank when we want to refresh it. Okay, so you have to be careful with that. And this is actually, it's already orchestrated in the memory controller. So the memory controller, whenever it sends refresh command, it directly stops sending other commands until I get feedback that this is done, or I wait that interval, which I know that the DRAM will be available after that, and then I keep sending the other commands to the DRAM. All right. Now we talk about DDR4, but there are DDR5. Now let's see what is the difference in terms of the performance, or what we call as a bandwidth, okay? The amount of data I could read from those memory per second. So this is the bandwidth I get from DDR4. We have about 32 banks, and the banks are arranged into group of 8. It means every 8 banks are sharing the exact same 3 buses, okay? So the data, the address, and the control. Now, if we go to DDR5, you'll see the increment, although double the number of banks, but the bandwidth, it's not double, right? And that's what we discussed. If you remember the plots for scaling the memory versus scaling the CPU processing speed, right? So processing speed is really flying, a rocket flying, and the memory scaling is really kind of sublinear or sometimes much less than that. Okay? Even if I double the number of banks, I still have problems, for example, of refreshing. So refreshing is stopping me because I have to hold back from accessing all banks when I refresh. So if I have more banks, now the interval will be much longer, right? Because I need to refresh all those banks. And that's problem really holding back the capacity or the bandwidth, even if I'm increasing the number of banks. And you can see with different configuration, this is still DDR5. The bandwidth, even with the latest, is still not doubled with the 15. We are barely with the 30 gigabyte per second. That is the server scale DDR5. All right, now a very important topic. Now, based on your imagination, we said the granularity to access the DRAM was a row. So we access entire row. And sometimes this row can go up to, for example, in this example, 1,000 byte. So imagine 1,000 byte, how many bits? How many bits in 1,000 byte? 8 times 1,000, right? Almost about 8,000 bits. Now imagine every command I send to the DRAM to read some data, I got 1,000 bits need to be sent in parallel, right? They cannot be sequentially sent, because if I need to wait for 8,000 bits to be sent, I need to wait 8,000 units of time. So normally we send them in parallel. But if we allow for sending 8,000 bits in parallel, what will happen? What will happen with the data bus? I need to have 8,000 wires connected to the bus. So imagine that. How many of you saw the cable that connects the SSD? Five. What we call? SATA. Excellent. We call it as SATA. How wide or how short? Two fingers, right? Or one finger width of the cable, right? It's very dense, very small, right, in terms of width. However, it's much faster than the older version. Do you remember the HDD? The hard drive, the older one, not the SATA. Have you ever seen the data width of the data bus? The gray color. It's a gray bus we connect to the old hard drive. It's really wide. This is what we see. This is the SATA. This is with the recent SSD. And this is the gray cable that we connect to old hard drive, right? How many wires do we have here with the number of those ports? So probably this is maybe 32 or so, and 32 here. So we have about 64 wires, if I count them correctly. You can count them, but roughly maybe around that number. And you can see every pin is connected to a wire. You can see the wire over there. It's clear, maybe. And all of those are the wire stacked next to each other. So imagine with 8,000 wires, what will happen inside the machine? You'll have this big data bus, right? So this is, in reality, is not happening. Why is that? Because of something we call as SerDes. SerDes. What is it? Serializer, the first three alphabets, serializer, deserializer. Okay, what is it? Here's the data I want to send from one point to another point. Those are in parallel. Imagine we have 8,000 of them, right? 8,000 bits. Now I have here what we call a serializer. So I serialize all of those data. However, remember we said we don't want to send them sequentially. If we send them sequentially, and each bit like in one clock cycle, now I have to wait 8,000 clock cycle to get them. So that's why this is not normal mux. That's why we call it serializer. So it takes the data. If it is like this much of time for one bit to read, it squeezes the bit within very small amount of time and send many of them in the same clock. That's why we serialize all of them from 8,000 into one. And not only that, we compress, we squeeze the time for single bit with very high speed clock. So normally we use here much higher frequency than the original data was read with, okay? So normally we use what we call as a clock generator inside those communication. That's why the interconnect or the communication from one point to another point is not just a wire, okay? We have what we call as transmitter, and normally it has very high speed clock to send the data through those single or few lines, few wires, with very high speed, much higher than the original speed we have the data at, okay? And at the other side, we have the exact same clock to be able to read this fast data. So if this clock at, like, let's say 10 gig per second, and this one at 1 meg per second. So we use here a clock of 10 gig, again, with the same rate of the data itself. So with that, we are able to read it back and then send it to the original speed to the receiver. So here, the bit width equivalent to the original. And then this is how we reduce the number of wires required to send large amount of data from one point to another. Is it clear? Any question? This was my master's topic, my master project. So I have my thesis, you can read it. I have several papers, you can read about it. We did one of those designs. We have here, instead of using one clock, we normally have multiple of those clocks gradually increased or double. So here, the original data, you send it at the original speed, then you use double of that speed for the next level, so you can multiplex 2 times of that data path into 1. So you convert 2 into 1, 2 into 1, and then those 2 into another 1. So basically, you convert 4 wires into single wire, okay? You max 4 wires into single wire, and every time you do 4 to 1, 4 to 1, this is how you reduce the 8,000 into very few number of wires. The downside that you need very expensive clock generator, which we call as PLL, phased locked loop, in order to generate all those variable amount of frequencies. This is the paper, this is the thesis. You can read more about it. All right. Now, hopefully we are clear. Yes. No, the serializer, we are sending the data from memory to the CPU. So serializer from the memory, deserializer or decode the data, right? But we don't decode alone. Remember, there is speed variation. So we have to get the data back to the original speed in order for the CPU to understand it. Okay? So serializer, deserializer at the other side. Now, if we are sending data from the CPU to be written to the DRAM, we do the opposite. Serializer at the other side, send the data, deserializer at the receiver. And that is not part of the DRAM. This is part of the interconnect. Okay? However, still something very important with the DRAM interface itself. We will see it in a few seconds. But hopefully now, yes, please. Yeah, it should be different. Should be different, but should be equivalent to the receiver side. So they can communicate with each other correctly. They understand each other. If this is very fast and the receiver is slow, we are going to lose some of the data. It will be like sampling the data. So every once in a while, I could read one bit and miss many others, read another bit, miss many others. But if they communicate with the same speed, then I could cope with the amount of data. Yeah, the processor is used for computation, right? So whatever data used in the buffer, so the memory controller is going to tell me, this is the data I receive after I send this command. So I already know that this amount of data that I received through the data bus is for this particular command. And then it will send it to the instruction that require, or to the core that requires that piece of data, and then handle that data correctly. Of course, there should be some orchestration between the communication and the data I requested and when I receive it. Otherwise, I'm going to play with different type of data. Okay? Yes, definitely. There are a lot of clock generator in the system. I have some slides, but maybe in the next around 60 or so. I don't think we are going to jump into 60 here, but we will see the DDR5 from inside, and we will see a clock generator inside it. And it's about, I think, 1/7 the size of the entire DEM. Okay, it's a really significant part of the module. Okay, and not only that, we talk about temperature sensor, right? Not one, two. We also have other components that's relevant to Richard Hamming. We remember this guy, American mathematician, invented Hamming distance. Excellent. Hamming distance is a way of correcting a data once you transfer it from one point to another point. How you ensure that the same data I sent you from one point to another point was received correctly. And that's happening inside the DRAM. How many of you presenting papers about Rowhammer? There were 4 talks about Rowhammer or security. 1, probably you have partners, right, in the team. 2, okay, yeah, in those you will see something really important. That's why we have what we call error correction inside the DRAM module itself. But now this is not our point. This is not the topic that we are discussing today. But we will see that the DRAM is really not only about storing data, but we have many other components. We talk now about clock generator. We talk about the temperature sensor. And now we mention the error correction codes or error correction chip, which is responsible for solving the Rowhammer issue, for example. What is Rowhammer? Hopefully, when you attend the 4 talks, you will see it. This is a very hot topic, extremely hot topic, even today in the AI area, in the AI application, because most of them are using GPU, and now it's proven that also the GPU are exposed to Rowhammer attacks. So even the GPU itself. So all the previous work were about the DDR5, DDR4, and so on in the computer. But now there is a recent paper showing that they are able to do Rowhammer attacks also for GPUs, which is now becoming very risky. Imagine you store something in the DRAM, and then you could flip any bits you want. You could do attack to the memory directly and change the data itself. It's not about changing the data, so the data might not be sensitive, but sometimes you store a public key or private key inside the DRAM, right? Because you are loading it, you are reading it when you go to access servers, for example, SSH or so. And imagine you flip one bit in that key. You prevent the user directly from accessing something very important. And this is a way for you to hack the system because you prevent all users from accessing that system. This is a very well-known attack called Rowhammer. There is the Spectrum attacks. I think there is one paper in the list about Spectrum. There is many other computer hardware attacks. Those are not cyber attacks. Okay, they are not software attacks. They are hardware. So you go to the hardware component and you attack the particular hardware based on the properties that you know that this DRAM is exposed to, for example. So this is just like a motivation for you to attend these 4 talks. Okay. All right, we go back to our story. We have the matrix of columns and row. Remember, we always access one row, and then you can do whatever you want with that row. You can access the columns in that row and so on. And you move that row to the row buffer. The row buffer is a sense amplifier, so it senses the charge and amplify the charge again, and then send it back to the row. Now, imagine that we got an address from the memory controller asking you to access row 0 and column 0. What you would do? And those a lot of famous question in the exam. Give me the sequence, how I would communicate with the DRAM if I want to access row 0, column 0. So the first step, the memory controller should issue a command, right? Which is read or write. In this scenario, I want to read whatever stored in 0 and 0. So I send through the address row 0, column 0, regardless the encoding, how we encode, how many bits for row, how many bits of column, right? It depends on the interface that we are sending. And I send through the control, what command? If I want to read, what are the 3 steps I should do? Activate, then read this address, and then pre-charge. So let's go. Now, first, remember, I cannot read columns. So forget about columns. I read rows first, and then I move to the column. So I take the row address. I send activate command to the row. Now I open it. What does it mean activated? Means the word line is connected to all cells in that row. The word line is connected to all cells. Now, I connect the bit lines vertically to those cells in that row and move all the charge to the row buffer. Remember the scenario of half VDD, and then if there is a small margin increased by that, then the sense amplifier directly amplify that little increase to the half VDD. Still have 15 minutes. Right? So we sense that little difference, and then we could know if it is 1 or 0. We already have the data, and then you can do anything with the column. For example, now I want column 0. I go with the column max, and I get only that small portion of data from the row buffer. Now, imagine that I send again another address, which is row 0, column 1. What should I do? Now, remember, the memory controller is smart. Already knows that I sent you just right a few seconds ago a command to read 0 and 0. Now I want a 0 and 1. So, oh, it's the same row. So wait, DRAM, don't close the row. Keep it open, keep the data in the buffer. I'm coming. I need to read the next column. So I go to the row buffer. I don't access the memory matrix at all. And this is a famous problem with the student when try to answer. They make mistake in here. You don't check the matrix at all. I check the row buffer first, and if it is a hit, then I directly go and encode the column that I want to access, which is number 1. Then I access it. I send it through the data bus back to the CPU. I get another address, row 0, column 85. Oh, same row. Wait, don't close the row. Go to the row buffer. If it is a hit, decode the column that you want, get it into the data. Now I get another address. Oh, now it's row 1. It's no longer the same row. So what should I do? Get back the row to its place to refresh that row, and then give me the new row. Remember, I cannot access columns. So don't access column directly. That's a conflict. Get it back, charge that row. Now access the new row, get it back to sense amplifier, and then decode the column that you want, get the data, and done. Okay? Any question? All right. This is a picture of single DRAM chip. Single DRAM chip. But this is very old. Okay? This is no longer in use. But normally with more updated DRAM, you don't have any insight about what's inside it. Okay? So you'll have little information about how the architecture from inside and so on. Because there is really big race between companies, especially Samsung, for example, and many companies producing those DRAMs. Okay? Normally, you have very little information about the architecture, the what's inside it. For example, ECC. You have no information how those DRAM corrects the error. Nobody will tell you what algorithm, what are the things. There are some papers try to do reverse engineering. They try to introduce the error themselves, and they observe what is the corrected value. And based on the pattern, it is randomly fixing that, or there is a certain pattern that they try to prevent. They could suggest what kind of algorithm implementing the error correction. Okay. However, Let's see what's inside this chip. Remember, this is a chip, not a single bank, not a single array, not a single matrix. So this is a bank, has many sub-arrays, and each sub-array is the sub-matrix we discussed. So if we see here, this is the address. We have 14 bits for the row address and 10 bits for the column. What does it mean? How many rows we can access if we have 14 bits for the address? Yes, we'll get chocolate. 14 row? No. This is binary, so if it is 14 bits, so this is 0, 0, 0, 0, 0, 0, 0. This is the first address, right? Second address 1, 0, 0, 0, 0, 0. Maybe. How you calculate it? Y to the power 4. Excellent. So 2 to the power 14. Because all the permutation of that number, all permutation of number of width 14 bits. So you start from 0, 0, 0 all the way to 1, 1, 1, 1, 1, 1. And this is the last address that you could get from the DRAM bank itself. So 2 to the power 14, many rows that you can target. Every time you can specify address for certain row, and then you can access. Okay, excellent. You got the chocolate today? No? We should make a record who got the most chocolate, right? Okay, likewise with the column, how many columns in the matrix? 2 to the power 10, right? So I could access with the number of width 10 bits, all zeros, that's the first column. And the very last column in the matrix is 10 bits, all ones. That's the last address that I could access. So how many permutation I do have? 2 to the power 10. What else do we see from here? So I see a mux to understand the address where it went for which bank, right? I see many of those banks from 0 to 7 mean I have 8 banks in this chip. Remember, a DEM has ranks. The ranks has chip. And each of those chip has 8 banks, okay? So if I'm using 2 chip, if you see 2 black boxes in the DRAM module, means it has 2 chip. And in this example, it has 8 banks in the chip, okay? How large the bank itself? We already talked about it, which is the number 2 to the power 14 times 2 to the power 10. That is the size of the bank itself, okay? Now we have sense amplifier. This is how many bits I could read, 8,000 bits. I send to IO. IO do some decoding for the column, and then I could get maximum 32 bits out of the 8,000. Okay, so the hardware in this chip allows only to access 32 bits out of this many bits. That's in one cycle. So in the second cycle, I got the second 32. Third cycle, second 30, third 32, and so on. So the granularity I could access those banks is the row, but I'm limited to 32 columns. So I get the entire row, right? But I can access only 32 bits per cycle. And not only that, these 32 will be downgraded into, you'll see the 32 bits moving into read latch into 8 bits, 8 bits, 8, 8. Okay? So now, that's why I call this chip as 8-bit DRAM chip. The output is 8-bit per cycle. So every time I request data, I'm able to read the entire line, but I cannot fit it into the IO. So I get only 32 bits out of that, and I latch it into 4 bursts of 8 bits, or forced packages of 8 bits, and then send one by one at a time. Okay? So every time I access the chip, can access single bank at the time and single 8 bits out of each bank, right? Now, of course, with the advanced chip, you could access up to 64 bits in the time. Okay. So I think maybe next lecture we will visit DDR5. I have a lot of information about DDR5. We'll see the differences between whatever we explain and what we have in the new modules, which is recent. The current one is DDR5. Remember that. If you want to buy a new laptop, always should have DDR5, not DDR4, not DDR3. And it has really significant difference. So normally it's a backward compatibility, meaning that if you purchase DDR4, it should fit with the PCs or computer that are compatible with DDR3, right? But now with DDR5, it's not backward compatible. Okay, so you cannot fit it in the same motherboard that support DDR4, for example. Why is that? Because they add a lot of modification. They increase the number of pins in the DRAM DIMM itself. So the DIMM itself, or the chip that you place in the motherboard, now it has many additional pins compared to DDR4. That's why it doesn't fit in the slot. Okay. Multiple chips operated together to form a wide interface. Someone could ask, if each chip provides only 8 bits per cycle, that's really ridiculous. Nothing, 8 bits. How I could get 16 gigabyte per second, as we saw in that plot. So if it's providing only 8 bits per cycle, how I could do that? Normally, the DRAM, they don't use single chip. So a single chip will provide you 8 bits, but they provide many DRAM chip in the same rank, and all those ranks provide data at the same time. So all of them will give you 8 bits per cycle. Now you have 8 bits from the same chip, 8 bits from the second chip, 8 bits from the third chip. You combine them, you get the 64 bits, for example, from all of them at once. And that's why the rank will share the data, the address, and the control. So all chips in that rank will know the exact address that they are looking for and what command I should process now, whether it's read, write, activate, pre-charge, and so on. So all chips comprising a rank are controlled at the same time, respond to a single command, and share address and command buses, but provide different data. Okay, because of course each chip has its own data, but they provide me the same data to be shared on the data bus. A DRAM module consists of 1 or more ranks. That is what we have the DIMM with all these ranks, and this is what you plug into your motherboard. If we have chips with 8-bit interface to read 8 bytes in a single axis, use 8 chip in a DIMM. I have an example for that. You don't understand, but remember, now the chip we discussed has 8-bit as output, although it can read 32 bits directly. So to provide you 4 packages or 4 batches with single request. Whenever you request the data, it gives you directly 32 bits, but divided over batches of 8 bits. Let's see this example, and maybe we can end up the lecture. Do you remember the cache story? Are you sure? All of you? We don't have to repeat again? OK, perfect. Imagine that the cache or the memory controller asks the memory to give me 1 cache block. And in this example, the cache block, the capacity is 64 bytes. Okay? And the memory controller already sent that command to the DRAM. Now remember, the DRAM can send 8 bits per chip. What I want is 64 bytes of data. So what is the amount of time it's needed and how many chips I'm going to use? In this example, let's use 8 chips. Remember, each chip provides 8 bits per cycle. So now I send the first command to read row 0, column 0 from all of them, all chips at the same time. Remember, they are all sharing these 3 things. So they already know what I'm looking for. Now, first thing, I cannot access the column, so I have to access the entire row. I get the entire row, and then I get column 0 from all of them. Each chip provides me 8 bits from the column, and that's why I have a bus, a data bus of width 8 bits in each chip. So each of them will give me 8 bits, and I have 8 chips. That's 8 times 8 equals 64 bits, which is 8 bytes. Okay? That's happened in the same cycle, same moment. I don't have to wait concurrently, okay? But I'm asking for 64 bytes, and those bytes are consecutive to each other. They are next to each other in the same row, for example. Now I get that data, I get the 8 bytes, I send them to the cache. Now I'm sending the next because I'm still not saturating the request. I'm asking for 64 bytes. Now I go to the same row, I ask for the second column for all chips at the same time. I get the next 8 bytes, I move on until I get 64 bytes. Now how many times do I need to get that? Every time I access the 8 chip, I get 8 bytes. I need 64 bytes. That is 8 times that process. And remember, every time I activate, read, pre-charge again, move on to the next row. But if I'm accessing the same row as in this example, all in row 0, then I'm saving a lot of time by not pre-charging again, because the row is already fetched in the row buffer. So I just keep accessing the columns next to each other, because I'm accessing the entire block of data, which is, I'm sure it's next to each other. However, there's a problem. Here I'm trying to maximize the performance by accessing all chips at the same time. Now the question, how do I divide a single block of data over multiple chips such that I access all of them in parallel? Now imagine this data in row 0 in here, and this data in row 0, this data in row 0 are all related together. So originally, they are mapped into the hard drive or the storage or the SSD as a page of all these data next to each other. So I have row 0 from first chip and row 0 from second chip. They are really should be within the same matrix or below each other, underneath each other. Now, who maps all these data from the storage into different chip, and how we map them into different rows, how we map them into different columns, such as we maximize the performance? That is really open problem still until now, because it does not depend on single architecture. It really depends on your data itself. We discussed last time row major optimization, right? Which is a loop interchange. We change a loop, the swap, the inner and the outer loop to solve this problem, how we can access all rows at the same time. But sometimes, as in matrix multiplication, we cannot address that, right? We cannot get all rows. So we have to mix rows and columns. And that was for caches. But the same story for here. How we can map those rows for single matrix that we are going to access to the cache, how we can divide the one matrix over all these chips such that we access all of them in the same cycle. Now imagine the matrix that we are accessing, or all this data, the 64 bytes, is located entirely in chip 1 or chip 0. So the data is not divided over chips. Now, what is the number of cycles we need to access all these chips at the same time? So every time we access one chip, we get the 8 bits, and all the other bits that we get from other chips are trash, not related. So instead of now 8 cycles, how many cycles do we need? 64. Excellent. Did you get chocolate? You answered a lot of things today. You didn't get any? So you can see the optimization by just changing the layout of the data, by mapping the data to many chips or to single chip, how that affects the performance of reading that data. Although the DRAM device is still the same, the bandwidth, the technology, everything the same, but just by playing with the data where we should place it in this chip or that chip, affect directly the performance of fetching those data. All right, we can end now. We have a lot of slides to discuss about DDR5, so hopefully it will be interesting for next lecture. Please, let's take attendance now. And let's see who's online. So do you have any question before we end up? All right, hopefully that means all clear. Okay, thank you so much. I'll see you next week.